Section 3.3. In the previous lecture, we covered two sections. In 3.1, we introduced some preliminary and fundamental concepts related to the family of ODEs we're focusing on, LHCC ODEs. In 3.2, we introduced a method for solving a specific type of LHCC ODEs. To recap 3.2, I've outlined the procedure we developed in that section. So here we've got sort of a 5-step process. I just want to talk through this real quick. Step 1, we assume our solutions have the form y equals e to the rt. Step 2, we plug y and the appropriate derivatives into our differential equation. Step 3, we do some algebraic simplification. And as we saw in the last section, we only did 2 examples, but in both examples it was pretty clear that every time we do that algebraic simplification, the left-hand side of our original ODE will turn into what we called the associated characteristic polynomial. In step 4, if our characteristic polynomial has 2 distinct roots, we call them R1 and R2, then that means we have 2 functions. Y equals e to the, remember, y equals e to the rt is what we're assuming the form of our solutions is from step 1. So if I get 2 r values, then I'll have 2 solutions. We call them y sub 1 equals e to the r1t, and y sub 2 equals e to the r2t. And both of these functions are solutions to our ODE. And then in step 5, we want to merge those 2 separate solutions into one general solution. We did that by taking what I've called here a linear combination. Remember, a linear combination is kind of just a fancy way of saying I'm going to multiply each solution by a scalar and then add the 2 resulting components. While the first 3 steps are pretty universal, we could apply them to any LHC differential equation. Steps 4 and 5 can only proceed if the property we stated here is satisfied. The key feature here is that we have 2 distinct real roots, R1 and R2. As I pointed out at the end of the last lecture, there's no guarantee that this will be the case. In fact, this case, where our quadratic has 2 real distinct roots, is one of 3 possibilities. Another possibility is that our quadratic has 1 real root that's repeated. You'll explore this case in an upcoming homework problem. The third possibility is that our quadratic has complex roots. That's what we're investigating in this section. Let's get a sense of what issues can arise by looking at an example. Example 1. We know that if we implement steps 1 through 3 outlined above, the left-hand side of our LHCC ODE will be transformed into the associated characteristic polynomial. In the name of efficiency, I'll just jump straight to that polynomial. If you're unclear how I've generated this characteristic polynomial, take a look at the previous section's lecture. And in the examples we did there, we demonstrated the process that transforms from the differential equation to this algebraic equation, to the characteristic polynomial. This yields a quadratic equation that I would normally try to factor, but it doesn't appear this will factor. So I can use a quadratic formula to find the roots of our characteristic polynomial. And as you might have guessed, our roots are complex. That is, we've encountered the square root of a negative number in our roots. As you're familiar with, we're accustomed to representing that square root of a negative. In fact, we'll break this down and isolate the square root of negative 1, and we refer to the square root of negative 1 by the symbol I. So I would say the roots of our characteristic polynomial are r equals negative 1 plus or minus 2i, as I've got written here. It's worth noting that since the square root comes after this plus or minus sign in the quadratic formula, complex roots will always come in a pair like this. Some real number plus and minus some imaginary number. So we have these 2 separate r values. We can write them separately. R sub 1 equals negative 1 plus 2i, and r sub 2 equals negative 1 minus 2i. I believe we've done all the algebra correctly, but it does feel a little strange in this context to have complex r values as we have here. Let's scroll to the next page to explore these roots a little bit further. In the first paragraph on this page, I just reiterate the comment that I made a second ago, that if we do get complex roots, they'll always come in what's actually called a complex conjugate pair. So the roots will always have the structure, if they are complex, some real number plus or minus this imaginary number. Well, it's actually a real number, mu, multiplied by I. This notation, r equals lambda plus or minus mu I, is going to be the primary notation we use to reference complex roots to our characteristic polynomial moving forward. So let me move forward with solutions in this general format. Let's suppose we've got complex roots to our characteristic polynomial, and we know that they'll have the form lambda plus mu I for what I've labeled here as R1, and lambda minus mu I for R2. Recall that these R's are supposed to be coefficients in the exponent of solutions. So we could write two separate solutions where I've put each r value in the exponent, the same way we did in the previous section. And then, as I've indicated in this next paragraph, we could imitate step 5 from above by creating a general solution out of these two by multiplying each by a constant and then adding the resulting components. So in a certain sense, this is technically our general solution. I want to manipulate this algebraically a little bit just to sort of isolate some of the different components. First of all, in these exponents, I want to distribute the t inside these sums. And then based on rules of exponents, that'll allow me to rewrite this single exponential expression as the product of exponential expressions. Let me show you what I mean. Here I've first just distributed the t into each of these sums. And now each of these sums has the form e to a sum, to two terms that are added, or in this case subtracted. It's equivalent to addition. If you remember by rules of exponents, I could rewrite that as two separate exponentials that are multiplied by each other. This is what that looks like. So again, on the one hand, this is technically an answer. On the other hand, I don't know how we're supposed to make sense of this complex exponential. Here I have e to the mu I t. Mu is a real number. T is my independent variable, so I assume it takes on real values. I is the square root of negative 1. So how do I interpret the fact that this component is imaginary? And I've got 1 in each of these terms. How do I graph this? How do I make sense of that term? Notice that these leading components do make sense to me. C1 is some constant. Lambda is a real number, so e to the lambda t, this component is real. It doesn't have this imaginary piece to it. So really what we need to focus on is these two that I've underlined here in orange. How do we make sense of e to the mu I t? That's exactly the question that I asked in the next part of the page. And in order to address that question, we're going to utilize something called Euler's formula. This is also sometimes known as Euler's identity. It states that e to the theta I equals cos of theta plus I sine of theta. Theta here is just kind of a generic placeholder variable for any value. As I've indicated here, I'm not going to go into the details at this point in the notes about a derivation or proof for Euler's formula, but if you're interested in looking at that, I have included it at the end of the notes. So let's go ahead and try to implement Euler's formula in the context of the solutions that we were just discussing. Actually, instead of focusing on this general solution, I want to back up and look at these two individual solutions. We've technically got y1 and y2, and I want to think of those two solutions separately. So let me go ahead and write y1. I'm going to do the same algebraic simplification that I did down here to separate the two exponentials. And then let me apply Euler's identity or Euler's formula to that solution. So here I have first separated my y sub 1, which was a single exponential, into two exponentials. And then I've just noted here in orange that in applying Euler's formula, I'm treating mu t as the u in Euler's formula because that's what's being multiplied by I up in this exponential. So then applying the formula to this exponential term yields these two terms in the parentheses. This seems helpful in a sense, but at the same time, I still have an I in my solution. And we said earlier that the whole issue is that we don't know how to interpret a function like this in terms of t that also has an imaginary number. And so while this is interesting, it doesn't necessarily address the main concern that I have in this context, which is how do I accommodate or modify or deal with this coefficient I? So the next thing I actually want to do is write y sub 2 in this kind of expanded form. And expectedly, it's very similar to y sub 1. The distinction here is that I've got this negative in between lambda and mu I, which means this exponent on this second exponential will be negative mu I t. So applying Euler's formula, instead of using theta as mu t as I did for y sub 1, I'll be using theta equals negative mu t, and that yields this solution here. Now, if you recall properties of these trigonometric functions, cosine of the negative of something is equal to cosine of that same thing. So this negative inside here actually cancels out in a sense. In a similar way, not the same way, but in a similar way, this negative inside the sign moves out front. This is just a general property of the sine function. So I can actually rewrite y sub 2 in this way. And so I have highlighted here the two solutions, y sub 1 and y sub 2, that I know are solutions to my differential equation. Next, I want to apply those two key principles that we saw in the last lecture. Specifically, we know that if I'm dealing with a linear homogeneous differential equation, then I know that any constant multiple times a solution is also a solution. The second important property that we highlighted in the last lecture is that if I have multiple known solutions and I add them together, the sum of those solutions is also a solution. So I'm not quite satisfied with my y sub 1 and my y sub 2 here because they both still have this I in them. And so I want to try to eliminate that I by using those two properties. I'm going to need to manipulate y1 and y2, add them together, multiply by constants, and I don't have anywhere near enough room in my notes, as usual. So I'm going to erase what I have written here and just rewrite this expression for y1 and y2 for reference. So what I want to do next is I want to construct new solutions using those two principles that we just highlighted. If I use y1 and y2, I know that I can multiply them by any constant, I can add any known solutions, and whatever I get through those operations will also be a solution. To start, let me simply add these two equations. Since I know y1 is a solution and y2 is a solution, when I add them, I know that the result will also be a solution. Notice that adding these, there will be some nice cancellation in here. I'm kind of skipping some steps algebraically because maybe I should distribute this exponential back through, but confirm on your own that the algebra that I'm doing here is valid. When I add these two solutions, I claim I get 2 times e to the lambda t cos of mu t. So we know that this is a solution of my differential equation. Let's call that y sub 3. Well, I also know that I could multiply y sub 3 by any value, and the result would again be a solution. So let me take 1/2 times y sub 3. Suppose I call that y sub 4. These names are not important. I'm just sort of indicating that each of these subsequent new functions is itself a solution to my differential equation. If I multiply this by 1/2, I simply get e to the lambda t cosine of mu of t. This is pretty nice. It's a pretty simple function. And notice this does not have I in it, like we said was a problem with my y sub 1 and y sub 2. I'm going to hold on to this function as one of the building blocks for my general solution. Next, I kind of want to repeat that same process, but before I add these two equations, I want to multiply them by a constant. The trick is I'm actually going to multiply them by the number I. Actually, I'll multiply y1 by I, and y sub 2 I'll multiply by negative I. So now this is a little strange because I'm multiplying by the square root of negative 1, but our principle from the last lecture still holds. If y1 is a solution to the differential equation, then any number multiplied by 1 is also a solution, even if that number is imaginary. So I know that the two resulting functions here will themselves be solutions. Let me go ahead and name them as I did over here. Maybe I can call this y sub 5 and this y sub 6. Again, the names that I'm giving to these new functions is not significant. I'm just using that as a notational device. So now I'm going to multiply y sub 1 by I, and I'm going to push that I through in a kind of strategic way. Specifically, I'm going to distribute it inside these parentheses, and here's what I get. So I've multiplied y sub 1 by I, pushed it in so that I've got I times cosine of mu t, and then notice over here, if I multiply I by this sine term, that'll give me I squared. And so we know that I squared is equal to negative 1, so I've gone ahead and made that substitution here. Performing a similar operation, remember on this second one, I'm going to take y sub 2, and I'm going to multiply by negative I. That gives me. Now this one's a little trickier because let's look at y sub 2 here. I've distributed a negative I through. So here I will clearly have negative I cos of mu t. And then when I multiply this sine term by negative I, the two negatives will cancel, so that'll give me a positive. But then I'll also have I squared. And as we saw in the previous step, I squared will turn into a negative 1. Again, I'm kind of skipping some steps here, so maybe you can try to work this out in a little bit more detail just to confirm that my calculations here are correct. So just to reiterate, I know that y1 is a solution, so if I multiply it by a number, the result will also be a solution. So y5, as it's labeled here, is a solution of my differential equation, and so is y6. Using the same rule we used over here, I know that I can add these, and then the result will be a solution. So let me go ahead and add y5 and y6. Suppose I call that y sub 7. Again, this may not be as clear as possible algebraically because I'm not distributing through this exponential, but hopefully you see that if I add these two cosine terms have opposite coefficients, and so those will cancel out. When I add the two sine terms, they have the same coefficient, so I'll have negative 2 sine of mu t, and then this exponential is along as a factor. Once again, I'm not a huge fan of that negative 2, so I can modify this y sub 7 by simply multiplying by, I guess in this case, negative 1/2. And I've been able to construct a function which I know is a solution to my differential equation, which not only has a kind of a similar form to the other solution that I identified previously, so that's kind of nice, but also between these two solutions, I have eliminated the imaginary value I, the square root of negative 1. We went through this whole process because the functions y1 and y2, which we started with, had those imaginary values in them. And so through these operations, we've been able to come up with two separate solutions which we know are solutions to the differential equation and which now have the I eliminated from them. So I'll restate this on the top of the next page, but just because I feel like we've accomplished something, let me go ahead and write that my general solution will be built out of these two, and the way that I'll build that general solution, as we did previously, is I'll put a constant on this first one and a constant on this second one, and then add those two together. So this function that I've put a green box around will be the general solution to my differential equation in this context. Let's go ahead and scroll to the top of the next page where I draw some conclusions and I state this a little bit more formally. Here in Theorem 1, I summarize the result of the calculations that we just did. It states that if the roots of the characteristic polynomial of our LHCC differential equation are r equals lambda plus or minus mu I. So the condition here is that we have complex roots of our characteristic polynomial. If that's the case, then the general solution can be written in this form. This is the form that you have to memorize. This is the form that we're going to go to as soon as we find that our characteristic polynomial has complex roots. So from now on, instead of reworking all of those calculations I just did on the previous page, we can go directly to this form of the general solution. Let's demonstrate that with example 2. In example 2, we're given a new differential equation here. It is LHCC. It's linear homogeneous because the right-hand side is 0 and the coefficients on the left are constants. So as with the previous example, I can translate this directly to the associated characteristic polynomial. And if possible, I'll try to factor this characteristic polynomial. In this case, it doesn't look like it will, so I'll utilize the quadratic formula. So as we'd probably expect, we've ended up with complex roots to my characteristic polynomial. In this case, I get the roots negative 1 plus or minus square root of 5i. Utilizing the notation that we had identified earlier, I'll call the real part of these roots lambda, and then I'll call the imaginary part, which is just this coefficient here on the I, I'll call that mu. Now, based on the derivation we did on the previous page, we can go straight to this general solution. I don't have to do any additional derivation. I can just directly utilize this formula for the general solution. Utilizing this formula in the green box, I get this general solution in my orange box. So I have plugged in lambda and mu appropriately. So this is the general solution of my differential equation. In many problems, I'll be done there. That'll be my final answer. In this particular problem, we are provided with initial conditions, and so I'll need to do additional steps to incorporate those initial conditions. Let me start with this y of 0 equals 2. Here I've plugged in t equals 0 into my general solution, and then I'm told that that should equal the value of 2. This looks like a pretty complicated expression, but fortunately, if you remember properties of these trig functions, sine of 0 just goes to 0, and cosine of 0 just goes to 1. We know this exponential on the outside will just go to 1. So actually, this entire equation just simplifies to c1 equals 2. It's convenient. And notice, in a sense, that will always happen if I'm given a y of 0 value, because the structure of my general solution here always has this exponential and then the cosine and sine. So what happened here in this first step, we can generalize. We'll state that in just a second. To plug in my second initial condition, I need to find y prime. That is, I need to differentiate this general solution. This is a little bit more involved, so let me go ahead and work through these steps. As I said, these calculations are a little bit more complicated. Here I have calculated y prime and just double check that I have correctly applied the product rule, since I've got a function here as well as this function in parentheses. And then once again, when I plug in t equals 0, most of the terms in this big complicated expression simplify quite nicely. Maybe it's worth pausing the video for a sec and just getting caught up with these calculations and just verifying that I've done everything correctly. Based on my calculations, we have a C2 value of 3 over the square root of 5. So we can incorporate those two coefficients and write my final actual solution. So here I've identified my final actual solution, which is based off my general solution from above, but which incorporates the given initial conditions. Before I move on from this example, let me just point out a couple features of this solution. First of all, in the parentheses, I have cosine and sine. I've got sort of strange amplitude coefficients. I have a sort of strange factor here that's going to modify the period. But basically, I look at this entire expression in the parentheses and I just think of this as oscillation. Just repeating up and down, increase, decrease. And if I wanted to, I could figure out the specific properties, exactly what the period is, for example. But generally, I'm just going to think of this parentheses component here as being some sort of oscillation. What about this exponential on the outside? Notice that this exponential has a negative coefficient up there in the exponent. So that means that this exponential is going to decrease, and then it forces this oscillation in the parentheses to decrease as t grows. So over here on the right, I've just noted that if we were to take the limit of this solution as t grows without bound, we would get 0. And then I've drawn just kind of a quick cartoon sketch of the properties that I was just trying to capture there, that there is some oscillation in this solution, but as t increases, this exponential is going to drive that oscillation to 0. On the next page, I've summarized a bunch of properties that we can glean from this example and a few of the previous calculations that we've done so far in this lecture. Here I briefly provide a few bullets that summarize some of the properties that we noticed or can notice from the previous examples that we've worked out. A few of these are things I've already stated, so I just wanted to have them here formally. This first bullet, for example, just reiterates that if we do have complex roots to our characteristic polynomial, they will come in a complex conjugate pair, which we will write using the notation r equals lambda plus or minus mu I. The second bullet is actually also just a restatement of Theorem 1. And it says that if we have complex roots of that form, then our general solution is going to have the form given here. So the first two bullets begin with the condition that our characteristic polynomial has complex roots. So when does a characteristic polynomial have complex roots? That's what this third bullet indicates. The third bullet says that the characteristic polynomial will yield complex roots when b squared minus 4ac is less than 0. This is should be pretty clear when you write out the structure of the quadratic formula, and you notice that this quantity, b squared minus 4ac, is a quantity that's under the square root. So when this quantity is negative, that will lead to complex roots. And then I've added as a small theorem a version of our general solution, which is directly in terms of the coefficients a, b, and c. If you look back, we wrote this previously in terms of lambda and mu, but if you look at the structure of the quadratic formula, we can identify exactly what lambda and mu are in terms of the values of the coefficients a, b, and c based on the quadratic formula. So all I've done here is I've done exactly that. I've translated this general solution from the lambda and mu variables that we introduced previously to be directly stated in terms of the coefficients a, b, and c. This is a little much to try to memorize, and so I don't necessarily recommend that you try to memorize this exact form. There will be a couple cases where we utilize this structure. The next bullet reiterates the point that I made previously, that if my characteristic polynomial has complex roots, then the solutions will demonstrate oscillation or oscillatory behavior. That means they'll increase and decrease with some set period. I've provided a little bit more detail in terms of the types of oscillation. We could have steady oscillation if lambda equals 0. Looking at the general solution from above, we note that here lambda is the coefficient in the exponent in a certain sense. So a lambda value of 0 will make this exponential term equal to 1, and so I will just have these oscillatory terms, sine and cosine, without any exponential increasing or decreasing the amplitude. So that's why I say here we have steady oscillation. If lambda is greater than 1, then that exponential is going to be increasing as t increases, and so my oscillation will increase. And then the other side of that coin is that if lambda is less than 1, I'll experience decreasing oscillation. And then I've noted that this expression mu, which could be broken down as square root of b squared minus 4ac over 2a, does in fact identify the properties of that oscillation. So the period or the frequency or the wavelength, which are all interrelated, can be determined in terms of that mu value. We'll see examples of that moving forward. And then in this last bullet, I just reiterate the point that we saw in the last example, that if my general solution is of this form that we've highlighted, and one of my given initial conditions involves a t value of t equals 0, then when I plug that into my general solution, most of the terms in this expression in my general solution will simplify quite nicely. So we already saw previously that this exponential, since it's to the 0th power, will simplify to just the number positive 1. Similarly, cosine of 0 will simplify to the number 1, and sine of 0 will simplify to 0. And so when I've simplified this entire expression, I just have c sub 1 equals k. And this works in general, and so this is maybe just an extra little shortcut that you could take when you're dealing with initial conditions. That concludes this section on complex roots of our characteristic polynomial when solving LHCC ODEs. I will just mention, as I noted above, there is one last page which shows a derivation of Euler's formula. For the sake of time in this video, I'm not going to talk through those details, but I encourage you to read through it if you've never seen the details of how Euler's formula is derived.